We now look at section 1.5, solution sets of linear systems. Now there are two types of linear systems we will tackle. One is homogeneous linear system and the other is non-homogeneous linear system. What is a homogeneous linear system? It is a system which can be written in this form: Ax is equal to 0, where x is a vector and 0 vector is of course a vector with all 0 entries. What will be the size of the 0 vector? That depends on the sizes of A and X, if you recall. So A, if it's the size of A is m by n, and the X vector has to have the size at least n by something. So n by, because it's a vector, so it will be n by 1. These two have to match in order to get the product. And then the resultant, which we are getting a vector again, the size of that vector will be m by 1, whatever is left. So this was matched, and what is left is the size of the resultant vector. So in this type of system of equations where all the right hand side is all 0, then always such a system has a solution x is equal to 0, and this is called the trivial solution. Okay, this is obviously a solution, and so it's called a trivial solution. Any non-zero solution, so this is the 0 solution, but any non-zero solution of the homogeneous equation is called the non-trivial solution. And we are often trying to find the non-trivial solution. So since we said here that always the homogeneous system will always have one solution, so therefore we can say a homogeneous system is always consistent. Consistent means it has at least one solution. And also the homogeneous equation Ax is equal to 0 has a non-trivial solution if and only if the equation has at least one free variable. So if there are free variables available, then the system may have a non-trivial solution. Otherwise, it will have just the trivial solution. So here in example 1, 2, and 3, the question is asking determine if the system has a non-trivial solution. In the second and the third, it says determine if the system has a non-trivial solution if the solution exists. So it looks like in the second and the third there is a trivial solution. Write it in parametric vector form. We will do that. So it looks like in the first case there is no non-trivial solution because they didn't say if the solution exists. Anyhow, so let us look at these examples down here. I have actually solved them already just to save time. So this is the coefficient matrix, and I augmented the 0 vectors from the right side of the equation system of equations there. So and started the row operations there. So first thing I did is make these two quantities 0. So this and this. So note here are 0, 0. Okay. And then the next thing I did was to make this quantity 0, which was already a 0, right? So I didn't have to do much here, but I made this quantity a 1 by dividing by 9, and then made this a 1 by multiplying by the second row by -1 here, -1 R2. So after that, instead of making this a 0, I jumped and make from the previous it will be more. So instead of making the -2 in the second column 0, I made these two zeros first. Okay, and then after that I made the -2 0. But final answer was that x1 is 0, x2 is 0, and x3 is 0, which means all components are 0. So our solution is 0, 0, 0. So you can write it as a triple, the 3 tuple, or you can write it as a vector. So you can, the solution is 0, 0, 0. So there is no non-trivial solution. The only solution it has is the trivial one. The second example had two equations and three variables. So you can see there will be a free variable here. Anyhow, I just took the coefficient matrix and then augmented the right hand side and started applying my row operations. The first thing I wanted was this is the pivot, and so I want a 1 in this place. So I multiplied the row 1 by 1 over 5 and I got fractions, but it doesn't matter. So now I want to make this entry a 0. So I multiply the first row by 3 and I add into the second row. So here is my action, and I performed the action and I got fractions over here as well. Again, it's okay. Now this is going to be the pivot, so I want to make this a 1. So I'm going to multiply by negative 5 over 29, so that negative become 1, positive. And so I ended up getting these here. Now one last thing we have to do, we have to make this quantity a 0. So performing the action, the row operation, and I end up getting this a 0. So now you can see there is no pivot in the third row. So there is and there is a free variable. So we say x3 is a free variable. So we expect that there will be the system will be consistent, mean there will be at least one solution. Okay. So now I read and write down the equation. So I can, from the first equation, I have x1 plus 16 over 29, x3 is equal to 0, which will give me x1 equal to negative 16 over 29, x3. Second row equation is x2 minus 4 over 29, x3 is equal to 0, which gives me x2 is equal to 4 over 29, x3. So both x1 and x2 are being written here in terms of the free variable x3. Now if you remember, I have told you that you can call x3 a t or an s something, and then use those these are called parameters, st, some other quantity, but mostly maximum you will use 2 parameters. So s and t are the ones we will use. Here I kept using x3. In the end I am using t, so just to make sure that you understand how we are getting where we are getting. So x, the vector x which we were looking for, remember that is the unknown vector which has components x1, x2, x3. But now I replace the x1, x2, x3 by the quantities they are equal to. So x1 is equal to negative 16 over 29, x3, that's what I wrote here for x1. For x2, 4 over 29, x3, and for x3 I have just x3. As you can see here, if I had taken it to be t, then it would have gone that way. So now after doing that, I see that there is x3, x3, x3 in all three places, in all three components. I have x3 here, x3 here, and x3 here. So I can pull out the x3. Okay. So I am left with, in the first place, negative 16 over 29. In the second place, 4 over 29. And in the third place, we are left with 1. So this is your, basically that is your answer. So, but often what happens is that this vector in the end that we get, we try not to have fractions there. So think about if we multiply the vector, this whole vector by 29. Remember, we can multiply by some real number. So I multiply the whole vector by 29. So I get rid of the fractions, and so my vector becomes negative 16, 4, and 29, and then here is t. But what is t? T is basically just 29x3, 1 over 29x3. So we call it t. So what we do, variable we take out, and in there we are left with only numbers. So that is our vector u. We can call it the vector u. So now we say so x is equal to tu. So this is the vector equation where u is this vector with components negative 16, 4, 29. So what is the solution? So basically we say solution is all the vectors of this type. Okay? But what are those? So it means all the vectors that are multiples of u, or from this presentation, this representation, you can say all linear combinations of u, which means all multiples of u, which means you are getting a line. Okay, so in R3, because we are in R3, we have vectors of dimension 3 by 1. So we are in R3. So we can say solution is span of u, or you can say solution is, so this is the physical or the geometrical explanation, and solution is a line through u, or through 0 vector and the u vector, and passing through the origin. Now it's hard to draw this line because it's 3-dimensional, and it's hard to pick the coordinates of the vector. So you may not try and draw or sketch this one, but if it's a 2, if we are in R2, then it will be a good idea to sketch the graph. Okay, let's look at example number 3. So we have the equation looks like this, only one equation. So first we look at three equations in 3 variables. Then we looked at an example where we had 2 equations in 3 variables, and now we have 1 equation with 3 variables. So what will happen, we will have 2 of the variables are going to be considered as free variables. So which one? Well, you can think of you can pick any of these as any 2 as free, but just for simplicity, we will expect we will take x2 and x3 are free. So these are free variables. So that now I can write that 10x1 equals 3x2 plus 2x3, which gives me that x1 is equal to 3 over 10 x2 plus 2 over 10 x3, or x1 is equal to 0.3 x2 plus 0.2 x3. Okay. So now if at this stage I want to call them S and T, maybe it will be easier. So let x2 equals s, x3 equals t. Then x1 will be equal to 0.3 s. Now s and these numbers get confused, so I put this to s at the end. So I make the s like this. Plus 0.2 t. So that I can say x bar or the x vector, which is x1, x2, x3, going to look like, so 0.3 s plus 0.2 t. Then the x2 is s and x3 is t. So now what we can do, remember, two vectors can be added if they have the same side. So think of this as sum of two vectors. So we are going to separate the ones which have the terms which have s in them. So because this can be thought of s plus 0t, and this third row can be thought as t plus 0 times s. So when I put the vectors as a sum of the vectors of having s in it and plus the vector having t in it. So I have 0.3 s and then s and then 0. Because in the third row there is no s. Plus, now I look at the t vector. So I have 0.2 t, and in the second line we don't have the t, so 0, and in the last one we have the t. So that I can write it like s into 0.3, 1, 0, plus t into 0.2, and there is no t in the second, so 0 and 1. So this is what we are getting. What are s and t? They are some real numbers. Now this can be called as u and this can be called as v. So what are we looking at? So we have written x is equal to s times u plus t times v. It means this is a linear combination of u and v vectors. So if you recall from before, what is the solution? So solution in words is all vectors that can be written as a linear combination of u and v. So geometrically, what does that mean? All vectors that can be written as u and linear combination of u and v gives you what? Or is what? It is the span of uv. So we say or the solution is the span uv. Now this is going to give you, if you recall from before, this is going to give you a plane passing through the region. This gives you, this is a plane passing through origin. Okay, so I will stop here because now the rest of the examples we will be looking at the non-homogeneous systems. So I'll have the second video for that.